Hi, I'm Josh Anderson. Today millions of fish may be choking due to dissolved oxygen deficits in streams after rainfall events. And the reason this may be occurring is that runoff from farmlands deposit excess nutrients into our waterways. And these excess nutrients provide food for algae growth, which in turn consume oxygen. Low oxygen contents in our streams could possibly be creating a deadly environment for fish like trout. Today we would like to look at what the dissolved oxygen concentration time series is in a stream after a rainfall event. The dissolved oxygen time series can be modeled as a first-order differential equation, which is a function of T time and dO, dissolved oxygen. Some parameters included in this problem are K sub D, degradation constant, chosen as 1 over 12 hours. K sub R, the re-aeration constant, chosen as 0.3 over hours, and L0, the initial oxygen demand rate, chosen as 5 parts per million per hour. For a runoff event, we estimate our stream to have 15 parts per million of dissolved oxygen, so our initial condition DO0 is 15 parts per million. Plugging in values, we have our governing equation in final form. Physically, this differential equation equates the DO rate of change to the consumption rate by algae and the re-aeration rate by moving water. Let's see if Anna can't help us out solving this problem numerically in MATLAB.
One is we're using 3 different methods to solve the problem. First, we have the Euler method, and then this is Euler, and we just estimate the next y at the next time step using the current time step. For the second one, we're using the predictor corrector. While our predictor, we use the exact same thing as the Euler prediction, and then with that we also do correction, which is here in this formula. And then the third method that we use is the Runge-Kutta, which MATLAB has a built-in function with that called ODE45, and then the output is T and DO ODE45 at DDO dt, which this is a user-defined function that we wrote, and this is the function with input as T and DO, and then the output is the change of DO, the change in time. And this is our time span, 0 to 24 hours, with our initial value of 15 ppm. And this is the code to plot for Euler method, and we also plot the predictor corrector and also the result from the Runge-Kutta. And as we can see in here, that the result matches pretty well for the 3 method because we use a pretty small delta t. And we also want to consider what's going to happen if we do not use a small enough delta t. So in this example, we use dt equals 24 over 100, and in this slide over here, we are showing the comparison of using dt of 24 over 100, and if we make dt to be bigger, which in this case 24 over 10, we can see that all of the methods kind of going in a different way, and this is not what we want. We want the 3 methods to give a very small error compared to each other. So delta t plays a very important role in this case. And after that, we want to know where during our DO that it will fall below 6 ppm. In order to do that, we have to fit a regression line first through our data points, and we have written a MATLAB code using polyfit with our x is the time and y is the DO, and using the 4th order polynomial regression. And after that, we can solve the continuous function using the polyfile, and we also plot that together with our data point. And then the next thing that we want to do is we want to find where T when DO is at 6 ppm. So then we use roots, and roots is nice because we only need to use the coefficients from our polynomial function, which we already store in our coef when we use the polyfit. So with this one, I was just moving -6 to the right hand sides because we set our equation to 6, so -6 over here. And then I just use roots for the coefficient over here, and then I choose using roots. Remember that we will have all of the roots that's possible, and then with this one I got an imaginary result. So this code, this line right here, I'm just choosing the non-imaginary results, and again I plot using fplot. This is where y or DO equals 6 in the black line, and then I also plot the curve, and then this is the result. That this is our data points, and then the pink continuous magenta or the pink line shows our regression line, the fourth order polynomial, and then this is where DO equals 6 ppm. And from our roots function, we get that at our 3.59, that DO falls at falls below 6 ppm and gets back up again at our 10 point, roughly at our 10.
To conclude, we found that the Euler and predictor corrector methods need to use a time step of less than 0.24 hours to obtain numerical accuracy when solving the dissolved oxygen differential equation and using the parameters chosen in this problem. Secondly, after a rainfall event, the dissolved oxygen content may sag below 6 parts per million for up to 6 hours, which puts an unknown stress on the fish. If you want to know what this feels like, try holding your breath for 6 hours. Thank you.